Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The secrets of the asteroid belt, the next frontier in space exploration. The asteroid belt, a vast region between Mars and Jupiter, is a relic from the early solar system, a place where planetesimals, small rocky bodies that were the building blocks of planets, never fully coalesced into a planet. Approximately 4.6 billion years ago, when the solar system was still in its infancy, dust and gas surrounding the young sun began clumping together to form planets. However, in the region now known as the asteroid belt, the immense gravitational force of nearby Jupiter continually disrupted these clumps, preventing them from merging into a single planetary body. This left behind a sprawling band of asteroids and debris, which we now know as the asteroid belt. The asteroid belt contains millions of objects ranging from small dust grains to massive bodies hundreds of kilometers across. Most of the belt's mass, however, is concentrated in just a few large asteroids, Ceres, Vesta, Pallas, and Hygiea, each of which is over 400 kilometers in diameter. Ceres, the largest object, is so large that it is classified as a dwarf planet, with a diameter of about 940 kilometers. Despite these few massive objects, the total mass of the asteroid belt is quite small, only about 4% of the Moon's mass, making it far less dense than often imagined. The composition of the asteroids varies significantly across the belt, reflecting the different environments in which they formed. The inner part of the belt, closer to Mars, is dominated by silicate-rich asteroids, known as S-type asteroids, while the outer regions, nearer to Jupiter, contain more carbon-rich bodies, C-type asteroids, and icy material. This gradient in composition provides a fascinating record of the conditions in the early solar system, showing how heat from the sun influenced the distribution of material and the formation of rocky or icy bodies. In addition to these types, M-type asteroids, which are rich in metals like nickel and iron, are also present, particularly in the middle region of the belt. Some scientists believe that these asteroids may be fragments of larger bodies that once underwent differentiation, a process where a body separates into layers of different materials, like the Earth's core and mantle, before being shattered in collisions. Throughout its existence, the asteroid belt has remained a dynamic and chaotic region. Gravitational interactions between asteroids, collisions, and perturbations caused by Jupiter's gravity have shaped its current structure. These collisions, which continue to this day, produce debris that can sometimes be thrown out of the belt and travel toward Earth or other planets, becoming meteoroids. These meteoroids offer a unique glimpse into the material that formed our solar system. In the study of meteorites, chunks of asteroids that survive their journey through Earth's atmosphere, has provided crucial insights into the composition of the early solar system. The asteroid belt, though often portrayed as a dangerous, tightly packed region of space, is mostly empty. The objects within it are spread out over a vast distance, meaning that spacecraft can navigate the belt without much risk of collision. However, Its scattered remnants tell a profound story about the solar system's chaotic beginnings and how giant planets like Jupiter influence the fate of smaller celestial bodies. This unique region of space continues to fascinate scientists, offering clues to our own planet's origins and the processes that shape the solar system as we know it today. Exploration of the asteroid belt has long been a key focus for astronomers and planetary scientists seeking to understand the formation of our solar system. While early observations of the belt were made using ground-based telescopes, it wasn't until the advent of space missions that humanity could study these ancient objects in close detail. The discoveries made by spacecraft in recent decades have reshaped our understanding of the asteroid belt, revealing a diverse and dynamic region filled with relics from the solar system's formative years. One of the first missions to explore the asteroid belt was NASA's Pioneer 10, launched in 1972, which passed through the outer regions of the belt on its way to Jupiter. Although it didn't stop to study any asteroids directly, its successful passage demonstrated that spacecraft could safely navigate through the belt. Pioneer 11, and later the two Voyager probes, would also pass through the belt without incident, laying the groundwork for future missions. The true era of asteroid belt exploration began in 2007, when NASA launched the Dawn mission, a spacecraft specifically designed to visit and study two of the largest objects in the belt, Vesta and Ceres. Dawn was the first spacecraft to orbit a main belt asteroid, Vesta, and the first to visit a dwarf planet, Ceres, providing unprecedented data about these celestial bodies. Between 2011 and 2015, Dawn orbited both Vesta and Ceres, sending back detailed images and scientific measurements that transformed our understanding of the belt's composition and history. At Vesta, Dawn revealed a heavily cratered, rocky world, with a surface marked by ancient impacts and large mountain formations. Scientists were particularly interested in Vesta's differentiated structure, which suggested that it had once been partially molten and may have had a molten core. Vesta's surface also showed evidence of past volcanic activity, which further pointed to a complex geological history. The data from Vesta helped confirm that some meteorites found on Earth, known as HED meteorites, originated from this asteroid, providing a direct link between Earth and the asteroid belt. When Dawn arrived at Ceres, it found a world very different from Vesta. Ceres, with its icy surface and signs of possible subsurface water, appeared more like a transitional object between rocky asteroids and icy bodies found in the outer solar system. One of Dawn's most surprising discoveries at Ceres was the bright spots in the Acator crater, which were revealed to be deposits of salts, likely left behind by water that had once seeped to the surface. This finding hinted at the possibility that Ceres, despite being a cold, distant world, might still have some internal activity and could have once harbored a subsurface ocean. The exploration of Ceres opened up new questions about the potential for water and other volatiles in the asteroid belt, and whether objects like Ceres could have played a role in delivering these essential compounds to Earth. Ceres, with its relatively high water content, has become a key object of study in the search for understanding how water arrived on Earth and what role asteroid impacts may have played in making Earth habitable. Beyond Dawn, other missions have also contributed to our understanding of the asteroid belt. In 2018, Japan's Hayabusa 2 mission successfully returned samples from the asteroid Ryugu, a near-Earth object that is thought to have originated in the asteroid belt before migrating closer to Earth. The samples from Ryugu, along with those collected by NASA's OSIRIS-REx mission from asteroid Bennu, are providing scientists with fresh material to study the composition and history of asteroids, particularly those rich in carbon and organic materials. These sample return missions represent the next phase of asteroid belt exploration, where scientists can bring pieces of these ancient bodies back to Earth for detailed analysis. Through the study of these samples, researchers hope to unlock more secrets about the processes that shape the solar system's formation, the role of asteroids in delivering water and organics to Earth, and the potential for these processes to occur elsewhere in the universe. The asteroid belt continues to captivate the attention of scientists, serving as both a window into the past and a gateway to the future. The exploration of this region is far from over, and in the coming decades, missions are expected to delve deeper into the mysteries of these ancient objects. Beyond simply understanding the formation and composition of the asteroid belt, future exploration will focus on a range of scientific and practical goals that could have far-reaching implications for planetary science, space exploration, and even the future of humanity's presence in space. One of the most exciting aspects of future asteroid belt exploration is the potential for in-depth sample return missions, following in the footsteps of Hayabusa 2 and OSIRIS-REx. These missions are already delivering invaluable insights into the material makeup of asteroids, and future endeavors will aim to target a wider variety of asteroid types. By sampling different objects in the asteroid belt, scientists hope to further refine their models of planetary formation and the role of asteroid impacts in the delivery of key ingredients for life, such as water and organic molecules, to the inner planets. There's a strong belief that continuing this research could provide definitive answers about the role asteroids played in making Earth habitable. In addition to their scientific value, asteroids are increasingly viewed as potential resources for future space exploration. Many asteroids, particularly those in the asteroid belt, are rich in metals and other materials that could be mined for use in space. With the cost and challenges of launching heavy materials from Earth to space, the ability to mine asteroids could revolutionize space exploration and open up possibilities for long-term human settlement beyond Earth. The presence of water in certain asteroids, for example, could be used to create fuel for spacecraft, reducing the need to carry fuel on long journeys. The idea of asteroid mining, once considered science fiction, is now being seriously studied by companies and governments around the world. Several private companies have already set their sights on the asteroid belt as a potential source of raw materials for space-based industries. These companies envision a future where asteroid mining supports the construction of space habitats, refueling stations, and other infrastructure needed to sustain a long-term human presence in space. The asteroid belt, with its rich diversity of materials and its position between the inner and outer solar system, could play a key role in this new era of space development. However, before this vision can become a reality, numerous technical, legal, and ethical challenges will need to be addressed, including how to conduct mining operations in space and who has the right to exploit these resources. The asteroid belt also holds the potential for deeper scientific exploration into planetary defense. While most of the objects in the belt are confined to stable orbits, A small percentage of asteroids occasionally get nudged out of the belt and become near-Earth objects, NEOs. Some of these NEOs pose a potential impact threat to Earth. By studying the asteroid belt in greater detail, particularly the mechanisms that cause asteroids to shift into Earth-crossing orbits, scientists hope to develop better predictive models and technologies to deflect or mitigate potential asteroid impacts. This research is critical for ensuring the long-term safety of our planet from the rare but potentially catastrophic threat of asteroid collisions. In terms of planetary defense, NASA's DART mission, Double Asteroid Redirection Test, which successfully altered the orbit of an asteroid in 2022, represents a major step forward. While DART was focused on a near-Earth asteroid, the lessons learned from the mission will inform future efforts to defend Earth from asteroid impacts, and much of that research begins with a detailed understanding of the asteroid belt. Understanding the composition, trajectories, and behaviors of asteroids in the belt will be key to developing technologies that can prevent collisions with Earth. Looking further ahead, the asteroid belt might one day serve as a crucial waypoint for crewed missions to the outer solar system. As humans venture beyond the Moon and Mars, the asteroid belt could provide valuable scientific stops or even serve as a staging ground for missions to the gas giants and their moons. The belt's relative proximity to both Mars and Jupiter makes it a strategic location for establishing fuel depots, research stations, or even colonies, depending on how our capabilities and ambitions evolve. The discovery of water and volatiles in some asteroids opens the possibility that these objects could support life support systems for future crewed missions, providing astronauts with water and oxygen while also serving as potential sources of fuel. This vision, though still far off, underscores the asteroid belt's importance not just as a scientific curiosity but as a key part of humanity's future in space. As we continue to push the boundaries of space exploration, the asteroid belt will remain a focal point of study. It is a region that holds the answers to some of the most fundamental questions about the formation of our solar system, the origins of life, and the future of humanity's expansion into space. With ongoing missions and new technologies being developed, our understanding of the asteroid belt is sure to grow, revealing even more about this enigmatic region and its role in shaping our solar system. The asteroid belt, long thought of as a quiet, distant part of the solar system, is now recognized as a dynamic and vital frontier for exploration, both scientific and human.